Hey, another session on reaction mechanisms. This one's going to focus on carbanions. If you're looking for carbocations or other earlier sessions, you can check them out. It's on the same playlist. We'll do free radicals and carbines and the rest of the stuff another time. So, what's a carbanion? Here, you've got a carbon with 3 hydrogens, and the fourth is a species Y that readily gives electrons to this carbon, giving it a negative charge. Why negative charge? We'll look at that. And this breaks away as Y plus. This species right over here is what we're going to focus on. Okay. Well, why would this form? Firstly, this is heterolytic cleavage. If you don't know what that is, look at the earlier sessions. Yeah. And this can happen if Y is less electronegative than C. Okay. Less electronegative. Well, that means that C is, ready to accept electrons. Okay. Fine. And that's not a very usual case, which is why these are pretty reactive species and usually short-lived as well. And Lewis bases. A lot of things in this last statement right over here. Note this down, Lewis base, because hey, it's got a couple of electrons that it doesn't really want, so we can give it away. Okay, so let's look at the hybridization of this. Before we go ahead and talk about formation and stability, one step at a time. We've looked at hybridization of carbocations in another video, check that out. Same setup here. In a ground state, carbon looks like this. Yeah, you've got 4 electrons in the outermost shell and a couple of electrons in 1s. Excited state in CH4, this is sp3 hybridized. You know this, we'll go over this again. And okay, if I empty out this last orbital, right, what happens? Well, you've got this H goes away, but the electrons from that CH bond break and come onto this. If CH4 were to break in this way, yeah, this is basically that Y plus that we said, right? So this breaks away and forms CH3 minus and H plus. Hypothetically, if that happens, that's what's going to do. So these couple of electrons are here. Now, is this still sp3 hybridized or does it become sp2 hybridized? Pause here, think about it. This is analogous to ammonia. Okay. Why ammonia? Well, ammonia also looks like this, right? It's got 3 hydrogen bonds and a couple of electrons. The only thing is it's not negatively charged. But if you look carefully, NH3 with a couple of electrons is isoelectronic with CH3 minus, giving you a little bit of extra information. Okay. Another way to make sure you understand that this also is sp3 hybridized. So both of these CH4 and CH3 minus are sp3 hybridized, which means that all carbanions are going to be sp3 hybridized. Okay, that's important. It's got a lone pair of electrons, negative charge because, well, carbon didn't have those electrons and hydrogen gave it away in this case. So there you go. All right. This is the structure of a carbanion. It's got trigonal pyramidal geometry. Remember, similar to NH3. Okay, that's what I do to remember it. They are nucleophiles. What does that mean? They like nuclei. Nuclei are positively charged, is negatively charged. They react with electrophiles. What's electrophile? Something like electrons. You know all of this. Okay. And they're pretty strong actually, Lewis bases, and they're very reactive. Right? Because it looks like it's a short-lived species, doesn't naturally form. I'm going to take a small detour to talk about something that may be bothering you if you're watching this video. You're thinking a little bit more than usual. Are these chiral? If I put a carbon surrounded by 3 R different groups, and here I've got a couple of electrons, is this type of carbanion chiral? Well, if you're thinking this, awesome, it's a little bit extra, but it's not, because there's a rapid inversion that happens between this form and the form that's on the right. What do I mean? Everything in chemistry or in real life is about energy, right? If the energy changes are really tiny to go from one form to another, they happen by themselves. That's exactly what this means, rapid inversion of carbanion. So it's very low energy and it's supplied just by molecular collision at room temperature itself. Similar to N of ammonia and amine molecules. Okay, so they are not chiral. Okay, detour done. Back to what we were talking about, which is formation of carbanions. That's the next idea. We'll do that, we'll do stability, and we'll wrap it up. Okay, how do these get formed? I gave you an example, right? That thing of H breaking away, that's a little tough to do. Okay. But if the H was acidic, that would happen easily. So this abstraction of proton in general is how this happens. Again, I said if it's acidic, it's easy. So if you have an option of couple of protons, the one that's most acidic is the one that'll go away. And this kind of makes it easy for us to figure out, oh, which carbanion is going to be stable. Because if the pKa value is low of the acidic hydrogen, then it goes away easily. You need to have an idea what is pKa, what is Ka. So ionic equilibrium, if you're not sure of that, please revise that. Yeah, this is just saying that the reaction of breaking away the proton is likely to happen, energetically speaking. That means that it has a low pKa and high Ka value. Okay, small revision bit here. But you'll see here that the order of magnitude of this pKa is pretty weird. It's pKa 17 and 30. You're not talking about pKa of 5 or 3, which is what you're used to, right? When you do regular acids and bases. So we're not talking about that. But still, everything in organic chemistry is relative. So this pKa 17 is more acidic. I'm going to write that down over here, although it's also going to come on your screen. It's more acidic than something that has a pKa of 30. Okay, in this species, acetaldehyde specifically. What is acetaldehyde? Well, it's it's an aldehyde. It's CH3CHO. Yeah, if you're not able to recognize this line diagram, you got to get used to it. Okay. Okay. How do I abstract a proton? Well, introduce a base. Base pulls the proton away. Which proton gets pulled away? This or that? It's this one. Why? Because this one is more acidic. That's the simple idea. Okay. In this case, the purple hydrogens, if you're able to see this, are more acidic than the green hydrogens. But why? I've given you the practical ideas to what happens in real life, but why? Can you figure that out with logic? Well, again, basics of organic chemistry and also what we do from ionic equilibrium. This attacking this hydrogen right here, a base, I've taken OH minus as an example, removes it, and now you see what happens. You get a negative charge. This negative charge comes here. These couple of electrons come here, and then this gets pushed onto this, giving it a nice negative charge here and this over here. Yeah, this is pretty stable. Why? I've got a negative charge on oxygen, which is already electronegative atom. Okay, great. And carbon's valency is satisfied. Perfect. Now, if I go and remove the other hydrogen, which is the one right next to the CO group, right? This is a carbon, right? What happens here? Look at this. I get a negative charge on this carbon, which is not great. This is an sp2 carbon, okay? And then when I move these electrons around, I get oxygen with 10 electrons. Not stable at all, yeah? So you see, we can do all of this behind the scenes, figuring out what's happening, or we can just look at the pKa values. And a lot of times in organic chemistry, in higher levels of organic chemistry, you're going to just do this, yeah? Because this reasoning, sometimes easy to do, sometimes a little bit difficult. But I hope you're convinced as to why this happens. Okay, awesome. There are other ways also to form carbanions. Yeah, one was what we just showed you. You could also take a metal, react an alkyl halide with a metal like lithium at really low temperatures. Yeah, in the presence of ether. That's a solvent over here. I'm not going to go into detail as to why the solvent is used or not. You can figure that out later online. But this is what happens, and well, this extracts this bromine, and here you go. You've got a carbanion over here. Okay. I could also take an anion and add it to an alkene or an alkyne. Why would I do that? See, an anion is pretty negative. You're going to tell me that, wait, hold on, alkene alkynes are themselves sp2 and sp3, sp hybridized, not 3, sp, which means that their carbons are electronegative as compared to a regular carbon. Sure, but this guy here literally has a negative charge. So you know what? It pushes this out, and you've got an anion here to boot. Okay, there's another way to make it. Okay, this was a bit extra, the last part, but the other two you need to know. How about the stability of carbanions? We're following the same structure as we did in carbocations, same way of doing things. Yeah, first we look at what they are, what's the formation, and what's the stability. So this is the last part of this. We're going to get done with this soon. Stick around. Okay, just like carbocations, we're going to look at inductive effect first. What is inductive effect? You know this, right? Pushing of electrons. Then we look at resonance effect, more stabilizing, and lastly something called S character. S character, yeah, sp versus sp2 versus sp3. This one has the most S character, right? 50-50. Here you've got 33% and here you've got 25%. You're able to figure this out? Revise chemical bonding. if you're not familiar with what I'm talking about over here. That's going to be important for you to do all of organic chemistry. Okay, let's do inductive effect. This is simple. You've got a hypothetical situation here. You've got OCH3, which is a species that really likes pushing electrons away. It doesn't want any. It's like it's got a lot of electrons, wants to give them away. If it does that, what I'm doing is I'm increasing the negative charge over here. Yeah, which is not good. If similar to carbocations, if you've got a plus charge, and if you push electrons towards that, that's great. So you're reducing a plus charge. If you remove electrons from there, you're increasing the plus charge. That's not stable. You need to negate the charge. Okay. In this case, you're adding to the problems. And also, you can see that you get carbon with 10 electrons. That doesn't make sense. Okay. So a plus I effect, if you have a higher plus I effect, the stability would decrease. And the example is of electron donating groups over here. I want you to draw parallel with the stability of carbocations over here. Which ones? Well, you did primary, secondary, tertiary. You know the order, right? Tertiary is really stable, then secondary, then primary. What do you think is going to happen over here? Here, I've got a methyl carbanion. Okay. So it's got 3 hydrogens attached to it. What if I take, let's say, a primary one right next to it? What's a primary carbanion? Well, I've got this group, CH3, this, and then this. What do you have here? Well, CH3 is also an electron donating group. So it's pushing electrons in this direction from right to left. Then it's increasing the negative charge. That's not good. So it's going to destabilize this species, which means that the most stable is going to be CH3 minus the methyl carbanion. And then you've got the primary, and then secondary, and then tertiary. As the number of these CH3 groups increases, the stability decreases. And this is the exact opposite of carbocations. Sometimes students messes up because they mug it. But I hope you will not mug it. We've given you a great detailed idea as to why this is happening. Okay, that was inductive effect. Positive inductive effect. So what would make it stable? A negative inductive effect, which means something that pulls electrons away. So this carbon here is electropositive. I'm not going to draw an arrow because I know arrows mean that electrons are moving. So let's just say this, pointy arrow. It's electropositive, which means that, hey, it wants electrons. If it wants electrons, it makes it stable. Also, these electrons, when they come here, this double bond electrons, they get pushed onto this, very stable. This is great. This is awesome. So, inductive effect, a negative inductive effect increases. If it increases, stability increases. For example, you've got electron withdrawing groups, like this electropositive carbon because of the CO group. That was a summary of inductive effects, right? And here I'm just going to write down again, CH3 minus is more stable than this species, which is more stable than this species, which is more stable than this species. If you're not familiar with what I've done here, again, primary, secondary, and tertiary carbanions. Slow and steady wins the race. Resonance effect, you know this. This is going to trump everything else. Here, you've got this species over here with a lot of benzenes around, and this although these are electron rich, but they're also like, okay, if you give me electrons in the same plane as the ones that are there over here, they'll happily take it away. And they're like, yeah, okay, awesome, that's great. These are going to be very, very stable. They're very stabilized because of resonance. And the more benzene you remove from this, it gets less stable. This cherry-picked example. This one's going to make more sense. Increasing S character and hybridization. Look at this. You've got sp hybridized carbon over here. This is 50%. This is 33%. I'm talking specifically of these negative charges here. And this is 25%. Okay. And I'm giving you this as a statement fact that, hey, you know what? Stability increases. But why? Check the pKa values. Okay. But why? Well, okay. You can ask a lot of whys here. The s orbital, electrons are closer to the nucleus than the p orbital. So, well, the electronegativity of this carbon, it increases with increasing S character. Simple. That's it. Don't stress on this. This is a very straightforward idea, and this is the logic right here. All right. So, summarizing the inductive effect, you've got all of this over here, right? And the resonance effect we've just looked at, and also the most awesome, simple idea the S character increases, which makes things more stable. So that was a wrap on stability of carbanions and carbanions in general. If you want me to make any specific video or any kind of question solving things, let me know in the comments. See you around.